Hey there. It's been long that, I revisited this series and I thought this would be the right time to kind of continue again. So yeah, welcome back. And what we're going to do in today's video is continue our journey to learning the C language. And one of the things I wanted to do was after we have taken a look at the idea of functions, I wanted to go in the direction of introducing the C keywords and then spending some time understanding some very fundamental ways in which C allows us to store data and operate on it. Formally, it is called data types. So let's take a look at that. Now, let's start our song and dance again, which is, just visit this URL, which is github.com/in-pyjama/c-ninja-listings. Once you're there, you'll see this repository. And then what we are going to do is focus on this button here and click this, and if you see code space here, then just click the triple dots here and click the open in browser. If not, then you will need to kind of you will need to press the button here and create code space, and creating a code space will take some time. Just bear with it. So if you see something like this, the name here might change. um, Go to the triple dots here and then click open in browser. So let me then get rid of all of this. Go ahead and click on open in browser. A new tab opens up, and it'll take a while, and yes, the code space is loaded. What I'll do is put it in full screen so we have all of the real to ourselves, the screen real estate. So in the previous video, we were working inside of the CASM directory, and these were the files that we had, and the foo file is open here. And let me just give you a quick recap. We looked at how what the idea of functions is. So we mentioned that, this is a function, let's say. So you feed in some value, it does some processing and kind of gives you an output, right? So input, put, and then it does some processing and then gives you the output. It's not necessary that you give the input, and it's also not necessary that the function gives you an output, right? We'll revisit this concept much later. But the idea here is we looked at a function that doesn't take anything, doesn't return anything, or rather doesn't give out anything. And we said that functions are a way in which you can group instructions together and, later on call them or invoke them. So here then foo and bar were the functions. Let me get rid of all the annotation. Yeah, so foo and bar are the functions. We mentioned that, the body of function is contained within open and curly brace. That's a way to group statements together in C. And then we mentioned that the function doesn't return anything. So we are using void as the keyword. Void essentially means, hey, this function bar returns nothing. And then in the return statement here, uh, we see that we are not having any value, let's say like 4, 3, 100, some random thing. We don't have any of that. We just have the return keyword followed with a semicolon. The semicolon we mentioned was a way to delimit a statement in C, right? That's like one complete statement, a meaningful statement that a C compiler can comprehend. And then remember I had drawn a diagram here saying input and output. Out. So the inputs are specified in the parenthesis here, between the parentheses. We'll take a look at this also a little later. But the idea then is that we talked about functions, then converted them into assembly and looked at what is going on. So now I want to continue to use this structure here, but then points about um, make some points about keywords and the idea of data types. So data types are important. This is what we'll play with. This is essentially a way to store values and manipulate those. the program manipulates the values that are stored. That's the general idea. Okay, so what we will do now, get rid of, okay, of this and jump to this directory here, which I created a moment sometime back before recording the video. And let me then walk you through the C keywords. And remember, our intention is that we just want to make ourselves familiar right now with what are the keywords C provides so that we can use them like a ninja. Okay, so there are total 32 keywords. And so these are like enough to understand all of the C language. Few people will argue that bool is a keyword, inline is a keyword, so on and so forth. That's like for the later standards. The original standard only had 32 keywords. Right? So we only take a look at those. All right. So recall that void and return. We have taken a look at that. Return is only used in case of the functions. Returning meaning exiting out of function, only used for that. So this one's complete. Void we haven't kind of discussed in full glory. So let me just put a start here. For today, my proposal or my plan is that I will cover what character means or char means, what int means, what float means. And I'll describe what they are in a while. But understanding the three keywords, my claim is, will enable us to understand lot many keywords later on. So what are those keywords? Auto, const, double, enum, extern, long, register, short, static, type def, unsigned, volatile. So we are talking about 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13-ish. 13-ish keywords can be understood once we understand just these three: 1, 2, and 3. And the remainder of the keywords can actually be grouped together separately, like bunch of them together, and they provide certain specific capabilities. For example, for loop, while loop, and somewhere there is do. These provide a way to loop or do things repeatedly in a number of times, kind of. Then break, case, default, these are also related, continue related, if else, so on and so forth. We'll revisit all of those later. For today, our focus will be on char, char, int, float, right? And then with this, let's move on to the concept of data structures. Oh, not data structures, data types. Okay, so what are data types? So any programming language provides us with a way to store data, right? Store data, save some results temporarily, so to speak. And then what happens is the stored data is what the program operates on. Right? Program operates on. So that is why we need to store the data. Okay, so C provides us with majorly integers, so saving those as ints, and it provides us with floats, right? So ints are used to save numbers like 1, 2, 3, 4, natural numbers, or actually integers, as the name suggests. So goes like from negative something, x, y, z, so on, so to positive x, y, z, or x, y, z, a, something, right? Some number from negative to some number positive. And then floats allow us to store number with the decimal, right? So 4.2, 1.0, things of those nature are stored using a float, right? So this is like a high level view of what int and float are. So what is a character then? So a character is essentially a byte. So recall that when we were talking about memory access and how systems are, as part of one of the videos in this series, we mentioned that the unit of memory access is a byte. So you can read a byte, write a byte, and a byte is essentially 8 bits. So you have got the 8 bits here, and that we a byte. And so when we mention char, we are essentially asking C to provide us with a byte to store. And obviously, what are the values that a byte can store? Well, it can go, total 2 to the power 8 possibility, and 2 to the power 8 possibilities are available. So 256 numbers or 256 different symbols can be stored here. Symbols meaning numbers. Yeah, this can be 1, 0, 1, 1, whatever, and that represents like some number. So that can be. So character is also an integer. It's just that we think of it a little differently. It's just that we get 1 byte. So if I were to do character XYZ, XYZ Piyush, for example, then this XYZ Piyush is a name, and that name is associated with a memory location, and that memory location is 1 byte long. Meaning, if I were to do char XY equals to, let's say, 10, then there would be some memory location where there is memory, a lot of bytes available. So one of the bytes, only 1 byte, will hold the value 10. That will be referred to by XYZ Piyush as a friendly name. Anytime I say XYZ Piyush equals to 1, so this memory location will, and that's the idea. Characters are a little more special. I'll talk about that. But just remember that 2 to the 8 possibilities, 56 entities or values can be saved there. Now the range usually is you can store a negative number starting from minus 128 up to 127. That's because, 128 negative numbers can be stored and 128 positive numbers, and 0 is involved in those. So half on either side. All right, that's one thing. And we'll revisit characters in a while again. So the int then is 4-byte variant. You can save many more numbers. Okay, I should mention that if you want to save 257 in a char, well, that is not possible just because you need 9 bits now to represent 257s, and we only have 8 bits. So, C would ignore, or the compiler would ignore that one extra bit, and it'll only store the 8 bits. All right, so if you want to store number like 257, then int is the way to go. So you can do int some random name, again follows the same naming convention as for functions. Can start with an underscore alphabet and can have numbers in between. So A6 underscore A6 is a perfectly good name, equals to, let's say, 258. So once we use this syntax, and we'll try this out in a while, I might use different names here. But once we do this, then there is somewhere, again, a memory location, which is represented by underscore A6, and 4 bytes are used to store the number 250. So that's the idea. And finally, there is float. Now, okay, about int, let me just conclude one more thing. So int, depending on the machine, the CPU and the compiler for it, can be either 2 bytes or 4 bytes. Meaning the range can be 2 to the power 16, right, negative 2, 2 to the power 16 minus 1, or it can be negative 32, 2 to the power 32, 1. Right? And this 32 and 16 represent 2 byte, 4 byte respectively. Straightforward? No problem. Now what we'll do is discuss about float. Float is special. So it is also 4 bytes long, and the way in which the data is stored is a little different. So if I were to say float p equals to 1.0, the bits here are stored in a way that the CPU interprets this to be a minus, sorry, not minus, 1.0, right? And then there is something called IEEE 746, I suppose. I need to check this, but IEEE 746 format, in which first bit represents the sign bit. Then there are 8 bits provided for um, the or exponent, sorry, exponent, and then there are, suppose, 23 bits, 1 bit, 8 bit, 9 bit, 9 plus 23 is 32, so 23 bits for the mantissa part, right? So this is the explanation. And then there is like a formula, minus 1 to the power of um, sign bit into 1 point, the mantissa, um, to, I suppose, e to the power minus 128 minus, sorry, the plus 128 minus something. Okay, let's just check that out real quick. So, okay, just a moment. Got the IEEE 6 standard. 746. Okay. 754 standard. Yes, very nice. So I can speak to this. Right. So we were talking about the IEEE 754 floating point format. That happens to be this. So out of the 32 bits, the first bit will represent the sign, a positive or a negative floating point number. The next 8 bits will represent the exponent, and then 23 bits will represent the mantissa. And this is how the CPU or the floating point unit will interpret the bits stored in the 32-bit value. So it would be like the first bit taken to the power of whatever the sign bit is. So if it is 0, this would be 1. If it is not 0, then this is minus 1, right? And then minus 1 into 1 point, whatever these numbers are, taken in the form of 2 to the power minus 1, 2 to the power minus 2, and so on. Again, let's not go super deep into it. Don't get confused. The idea is just to tell you that a floating point number is stored or interpreted differently, right? A 1.0 is not saved as 1. It's saved as some cryptic thing. Okay? So this is the mantissa then, and then the exponent, a minus 127. So whatever number is here goes here, subtracts, like we subtract minus 127, whatever that power is, translate, multiply, and then the number comes up. Very convoluted, but this will become clear. The idea was just to tell you how numbers are stored as floating point. All right, with this we can come back and let's now try playing around with these. So again, let's go back to full screen. Yes, working. Let me kind of set zoom to size. Nice. What I'm going to now do is first off copy all the files from the ASM C. So let me copy it and let me just paste it here, just so that our environment for the experimentation is set correctly. All right, so let me close these. We open up the foo.c here and let me in a little bit. All right. So what we'll do is we'll delete the foo function. We'll only work with, or actually, let me foo. Oh no, let me return it to be bar. The reason I'm letting it be is I don't want you to confuse foo.c and the foo, and they have a relation. They don't have any specific relation. Okay, Let's start off here. Much like the previous time, we have a linker script. We have a main.s that jumps to var, and then we have the makefile. This makefile will modify a little bit in a while, but let's just go ahead and first do this. So let's declare, so to speak, a variable char, can have any name, should just start from like a lower or uppercase letter or underscore. Let's just start it from, or just for random reasons, uppercase A followed by, yeah, this is all right. Now, what I should mention at this point is uh, char char equals to 10. This naming is not allowed because char or char is a reserved C keyword. But using it like this, in between, like it being a substring to something, that is all right. This is all right because all of this is one name and not just this. So that is allowed. Okay, perfect. So let's assign it a value of 10, or actually 97. This would be interesting, right? And 97 falls in the region minus 128 to 127, so we are all right. And then let's have an int. I'll just call it underscore my int, and then assign it the value of okay, 1, 2, 3. Right? And then let's have a float, and then call it like float underscore, p. This is also valid substring, and let's assign it the value of 1.0. All right, let's save this. Let me speak to how things need to be, what you need to be careful of. So again, the names here are same. The rules for that is same as that for the functions. Can start with an underscore or A to Z or to A to Z, and then it has to start with this. Can be, n can be arbitrarily long, and it can have numbers in between. It can be 6, 7, 8. For example, um, quickly modify the name and make it float 8 underscore p randomly. Okay, nice. So the other thing then is, remember, this space is not necessary. This space is not necessary. This space is not necessary. It's just of convenience for us. A C keyword or a C construct should either have a semicolon or one free space at least. And after that, one or more free space is considered to be just one free. We could have had many space here, but this is not allowed. Right? We wouldn't know what we're talking about because it cannot assume and separate out this first, what do you say, word. So hence there has to be a free space here, one single space at least, can be a tab, matter, just one white space. Then you may or may not have white space here. That's all right. Semicolon needs to be there once a statement or an is complete. So this, and this are three different statements. We have chosen to keep them on three different lines. That's not a necessary condition. So for example, I could have just as well done this, which will complete. All right. This is completely all right, but as you can see, it's just impossible to read this thing. In this case, we can still make out what it is, but longer programs is impossible to read the program rather. Okay, so we have this, and now I'm going to show you some makefile magic or some commands. Easy. All right. What we want to do is introduce one more variable here by the name of dump, obj dump ump. Then the utility that it points to is obj dump. And what I want to do is take this, put it right here, right? And you'll soon see why I'm doing all of this. So obj dump, we give it two options, -d and -s, is disassembly and assembly instructions. Then we say take the main.elf, and I'll show you what this does, and generate out of it, like output everything that you create, you were going to put on the screen, output all of it in main.elf.lst. And this extension, there's nothing special about it. It can be any extension. We choose it to be LST, so that means listing, and I'll show you how this how it helps. So let's then go here. I'll go to terminal and create a new terminal. So we are here. Then within that, let's go to the keywords directory, and we have all our files here. And what I'm going to do is simply do make all. I'm doing make all because of this. I want to execute this target, right? All right, so I do make all, and okay, it has printed a lot of disassembly, this, that. This command was executed, and as a result of this, the main.elf.lst file is created. And let me just quickly do make clean, so everything is gone, right? So there is lst mains, because we should also clear elf.lst. Let me do make clean again. The lst file is gone, so this was these are like the original files we started with, and then we do make all. Let's see, bunch of files are created. The elf.lst is what is of use to us, and the reason to that is it shows us, drum rolls at this point, so it shows us the C syntax as well as the assemblies. And this is one of the ways in which you can learn what assembly will a C program generate. For example, these three assembly instructions correspond to the line bar, right? The definition or declaration of the function. And then this line here, 21, is split into the two assemblies here. Then this line is split into these, and so on and so forth. Now, we are wanting to understand what happened, what is going on, kind of. And once you understand this, I think, the understanding of at least the three keywords would be, complete, and then we can experiment further. Okay, so what is happening? So this is our bar function that is understood. Okay, let me change the color pointer. I don't know, red. Sometimes. Okay, right. This and this. So we have the name of the function here, and then something's happening. There's an add immediate instruction, and it's operating on the SP. SP is the stack point. Right? So it's doing something with the stack point. Let's not go into the details, but then the stack pointer, at least it's assumed, is pointing somewhere in the memory, hopefully valid memory location, that is. And I'm saying hopefully, because who is setting the stack point? Right now, there is no part of code that we have. For example, this was the first line of code, and then rest of the code was here. And nowhere have we set the stack pointer. Right? But the compiler is assuming that there is a valid entry in the SP register, and if it exists, it is going to, not if, whether or not it exists, it is going to use the SP register to store some variable, store some value. And we'll come to how to set the stack pointer and who does it in later video. Point for today is the data types, few of them, character, integers, and all right. So somewhere there is SP, somewhere it's pointing somewhere, hopefully to the valid memory. And what is going to happen is it's saying that the S0 register will store a word 0. Okay. So S0, where it is storing some 28 and SP. So it simply means from SP, take the 28th offset, then store that S0. This we don't care about, so let's move on. Then it takes S0, then adds to that SP. Well, takes SP, adds 32 to it, and stores that into S0. So what is going on here is moving, it's kind of, taking a copy of S0, taking a copy of stack pointer register to operate on, and it's adjusting it to some free area somewhere, right? So it moved down by 32, then, did some, and then it moved up by 28 somewhere. It is pointing on the stack, right? Things are still on the stack. We don't care about the details of this. The summary is on the stack somewhere the S0 register is pointing. Okay. Now what happens? When we say, okay, character A underscore car equals to 97, notice this one, right? 97. So 97 is immediately loaded into the A5 register. A5 register has the value 90, right? And the SB instruction here means save a byte. And save a byte where? Oh, okay, A5 is that byte, whatever byte is available in A5, and store it on the 17th offset of the S0, from negative 17. So now we have the S0 somewhere, and it's asking it to kind of move backward, right? If the address is moving downwards like so, it's asking it to go 17 units from wherever it was pointing and store A5 there. If all of this was confusing, again, let me just make it super simple. There was a stack somewhere to which the SP was pointing. And we did some movement on SP, pilot did it, and there was this S0 register. And to the S0 register, it's saying, hey, go back 17 minutes and store a byte there, whatever happens to of A5, which is nothing but 97 libs. In short, this variable is going on stack. Okay, fine. Moving on, we have we have now an int with 1, 2, 3, and again, if you see, it's reusing the A5 register, storing 1, 2, 3 within it, and then saying, hey, now go a little further from S0. S0 was here. Initially, you went to 17 offset in the upwards or negative direction. Go a little further, and this was like this is like a byte. This 4 bytes, right? And hey, save a word. Remember, a word is 32 bits. So the compiler is now generating a save 32 bits. And that's what it means. So it's taking this 1 to 3 and saving it in 4 byte worth of. Right. And then if we still move on, then there is this float 1.0. If you see, it's doing something weird here. What it is doing now is if you see, it's nowhere doing 1.0. Doing some hex 80,000, and then okay, go to that memory location, then go to 60, do something, load word. But A5 gets the value, some bit pattern, presents 1. Then it's saying, okay, take that bit pattern, 32 bits again, and save it on the stack, 28 location. So long story short, this was too much to grasp, but long story short, note that a character would generate a storage of 1 byte. An int would generate a storage of 4 bytes, 2 or 4 bytes typically. In our case, 4 bytes, because of the RISC-V machine that we are dealing with. The compiler assumes that an int is 4 bytes. And similarly, a float is also 4 bytes store. That is the idea. Now, what I want us to do, notice that there is something. So it's saying, hey, load upper immediate in A5 of the 80,000. So we'll look for 80,000. See what it means. Does it mean anything? Yeah. Anyways, just loading in the upper immediate. Discuss this. So we have the A5 and the upper half of that is being loaded with this value, and then using this, essentially generating an offset, adding 60 to it. Suppose the value becomes this. See, let's try to find. Oh, very nice. Okay. Then doing something. So this is 4 byte, this 8 byte. Yeah. What is happening here? But some weird way in which it is encoding 1.0. Also at this point, I think I uh, should mention that, well, actually, never mind. Read my confusion. But okay, floating point is something we can revisit again. I think what I should have done, maybe we can set the stack pointer here and then see what will happen. Okay, that was like a chat for myself. Well, hopefully now you're convinced that what is happening here. Then very nice. Okay, so you have the stack. It's a rough imagination where 1 byte is a underscore char, then 4 bytes. Again, my stack is increasing downwards here. You know, don't bother about the assembly right now. This is just a visualization. And then underscore my int, somewhere point in on the stack. Then it's 1 to 3 and was stored here. Have float or p here, which is 0. And this bit pattern saved here would be of the format 7.4. Okay. So for now, I just want to leave you with char, int, and float as keywords. And what we'll do next time is take a look at the other 12, get some idea of how they can be used, and then dive into writing programs. So one other teaser that I want to leave you with then, just so that also have something to experiment with, is you can take these three, cut them, just them right here. And the question to ask is, so in the previous case, we noticed that all of these were stored on the stack. Question is, once I move them out, first off, this is valid. Question then is, where are these? Where are the values? And this is a very important question because depending on where you have the variables declared, they'll be stored in different regions of the memory. And what I can do is I can again suggest how you can store this. So modified the code, go back here, hit make clean, to make all whatever is rated .elf.lst, and then you'll notice something interesting, right? And now you don't see the values like 97, 123, and 1.0 within the body of the function, right? This is the body of the function. Written statement is fitting into this. The entry of the function is fitting into this. The question is then, what is happening? Where if you see there is all of a sudden char here, int here, and float here. Something's going on. We will revisit this in the later videos when we discuss about the dot data and the dot pss section and the initialization and all of that. And try and explore on your own. And the final thing is the third final thing. So the final thing is I want to explain a little more about the character. That is how you will see it being used. So typically, you'll notice that char, let's say x equals to something like so. So the single quotes here, what it dictates is, okay, take the a as represented by the ASCII standard or as represented in the ASCII table, and then store the associated integer value. I'll explain what this means. So store the associated integer value in the memory location and associate that memory location with x. And what A stands for in the ASCII table, go and open the chart table here, and let's look up what A stands for. So A stands for 65. So if I were to do char x A, then it essentially means in the memory called as or referred to in a friendly way as x, store the number 65. Right? So the 65 then is representing the ASCII. Again, we'll revisit all of this in due time. Not that you need to get everything right now. We'll just reiterate it many times. Okay, so so the ASCII value of A in decimals is 65. I'm storing 97 if you take a look here. So essentially in this case, tag that we somewhere we mentioned that there was a byte where 97, that 97 was associated with char or char lowercase, and this is storing effectively. Again, computers don't have any way to actually store the symbol A, so they represent it with a number and that number. And yeah, that's about it. So we will dig into the data types and other keywords in the next video, and then slowly start to look into what operations can we perform using these data types on these data types. How can they be combined together? We'll write a little more elaborate functions, learn something about function interactions, so on and so forth. And also do think on the question of who sets the stack point. We'll also revisit that. Then we'll again dig a lot more the C code using the mindset of an assembly programmer. With that, I'll see you in the next video, and thank you for staying along for this long. Take care. Bye-bye.